Hi everyone, welcome back to PRAKASAM tutorials. In this video, I am going to discuss about spectral characteristics of system response, that is power density spectrum of system response y of t and cross power density spectrum of input and output. And what is spectral characteristics of the system response? In my previous video, we have discussed about the temporal characteristics of linear systems and described in terms of autocorrelation function, cross correlation function, mean and mean square function. The spectral characteristics of linear time invariant systems are derived in this section, are derived in this video using Fourier transform. So this approach is conceptually valid. However, the evaluation of integrals may be difficult from the practical point of view. So that is the importance of the spectral characteristics of the linear systems. First, we are going to discuss about power spectral density or power density spectrum of system response y of t. And this is the statement of power density spectrum of the system response y of t. That is, so we prove that the power density spectrum SYY of omega of the response of linear time invariant system having a transfer function h of omega is given by SYY of omega is equal Sxx of omega into magnitude of h of omega whole square. So this is the statement of power density spectrum of system response y of t. So now here SYY of omega is the power density spectrum or power spectral density of the random process y of t, that is output of the system. Sxx of omega is the power density spectrum or power spectral density of the input signal x of t. Input signal x of t. H of omega is the frequency response of the system. So now coming to the proof, we know that the Fourier transform of the output correlation function is given by SYY of omega is equal Fourier transform of RYY of tau, which is equal to integral minus infinity to infinity RYY of tau e power minus j omega tau d tau. So this is the definition of the Fourier transform. The power spectral density and autocorrelation function of the random process y of t form a Fourier transform pair, and this is a mathematical expression. So we know that the autocorrelation function of the random process y of t for the linear time invariant system already explained in my previous video. So that is RYY of tau is equal integral minus infinity to infinity integral minus infinity to infinity Rxx of tau plus tau 1 minus tau 2 into h of tau 1 h of tau 2 d tau 1 d tau 2. So this expression already derived, already explained in my previous video. Okay, and substitute this RYY of tau value into above expression. Above expression means this equation. Substituting RYY of tau value into this equation, we get the power spectral density of the output y of t is SYY of omega is equal integral minus infinity to infinity integral minus infinity to infinity integral minus infinity to infinity Rxx of tau plus tau 1 minus tau 2 into h of tau 1 h of tau 2 into d tau 1 d tau 2 into, so that is, and this term is RYY of tau into e power minus j omega tau d tau. Let tau plus tau 1 minus tau 2 is considered as the t. So differentiate with respect to t, d tau is equal to dt. So RHS term of the above equation is arranged as integral minus infinity to infinity h of tau 1 d tau 1 integral minus infinity to infinity h of tau 2 d tau 2 integral minus infinity to infinity Rxx of, so Rxx of that within the bracket term is considered as the t, Rxx of t into e power minus j omega tau. So now here tau plus tau 1 minus tau t is considered as the t. From this expression, tau is equal t minus tau 1 plus tau 2. Then substitute the tau value into here this exponential term. So that one is e power minus j omega of t minus tau 1 plus tau 2 into d tau. D tau is dt. So this exponential term is split into three terms, that is e power minus j omega t, e power j omega tau 1, e power minus j omega tau 2. So the RHS term of the above equation is rearranged as integral minus infinity to infinity h of tau 1 e power j omega tau 1 d tau 1 integral minus infinity to infinity h of tau 2. Now here the exponential term is e power minus j omega tau 2 d tau 2 into integral minus infinity to infinity r x x of t e power minus j omega t dt. And this first term is the definition of the Fourier transform, and that is Fourier transform of h of minus tau 1. So that is h conjugate of omega. The first integral term is the h conjugate of omega. And second term is definition of the Fourier transform, that is h of omega. And third integral term is that is power spectral density of the random process x of t. So that is sxx of omega. But we know that a into a conjugate is magnitude of a square. So h of omega into h conjugate of omega is magnitude of h of omega whole square into sxx of omega. So this is the power density spectrum of the response y of t. So in this equation, we can observe that the power density spectrum of the output y of t is equal to the product of the power density spectrum of the random process x of t is multiplied with square of the magnitude response of the system. So that is syy of omega is equal sxx of omega into magnitude of h of omega whole square. And next spectral characteristics of the system response is cross power density spectrum of the input and output. So we know that the cross correlation function of the input and output is rxy of tau is equal rxx of tau convolution h of tau. So this is already explained in my previous video. So directly here I am taking the cross correlation function of the input and output is rxy of tau is equal rxx of tau convolution h of tau. In this equation, taking Fourier transform on both sides, we get Fourier transform of LHS term is equal Fourier transform of RHS term. Fourier transform of Rxy of tau is Sxy of omega. So using time convolution theorem, the Fourier transform of convolution of two time domain function is equal to multiplication of their frequency domain functions. That is RHS term is Fourier transform of Rxx of tau into Fourier transform of h of tau. Fourier transform of Rxx of tau is the power spectral density function of the random process x of t, that is xx of omega. Fourier transform of h of tau is h of omega. So sxy of omega is equal sxx of omega into h of omega. We know that Ryx of tau is equal Rxx of tau convolution h of minus tau. This expression is already explained, already derived in my previous video. So directly consider the cross correlation function of the random process y of t, x of t, input and output Ryx of tau is equal Rxx of tau convolution h of minus tau. Similarly, here also taking the Fourier transform on both sides. On RHS side, applying the time convolution theorem property, we get the Fourier transform of LHS term is equal Fourier transform of RHS term. Fourier transform of Ryx of tau is Syx of omega. So using time convolution theorem, Fourier transform of RHS term is Sxx of omega into h conjugate of omega. Similarly, the autocorrelation function of the system response y of t is Ryy of tau is equal Rxy of tau convolution h of minus tau. So this is already discussed in my previous video. Please refer that video. Here also taking Fourier transform on both sides. Fourier transform of LHS term is equal Fourier transform of RHS term. So the Fourier transform of LHS term is SYY of omega. So using time convolution theorem property, the Fourier transform of RHS term is SXY of omega into H conjugate of omega. But Sxy of omega is already derived here. And what is Sxy of omega? Sxy of omega is equal Sxx of omega into H of omega, and substitute this Sxy of omega expression into this equation. Substitute Sxy of omega expression to this equation. We get Syy of omega is equal Sxx of omega into H of omega into H conjugate of omega. So H of omega into H conjugate of omega is magnitude of H of omega whole square. Therefore, Syy of omega is equal Sxx of omega magnitude of H of omega whole square. Similarly, we also know that Ryy of tau is equal Ryx of tau convolution H of tau. So this expression is already derived in my previous video. Here also taking Fourier transform on both sides. Fourier transform of LHS term is Syy of omega. Using time convolution theorem property, the Fourier transform of RHS term is Syx of omega into H of omega. Sy of omega is already derived here, and Sy of omega is Syx of omega is Sxx of omega into H conjugate of omega. Substitute this expression into Syx of omega expression into this this equation. This equation we get Syy of omega is equal Sxx of omega into magnitude of H of omega whole square. So this is the concept of cross power spectrum or cross power density spectrum of input and output.